So in this particular situation, we're doing motion graphs and we're working on motions. So you want an acceleration on the slope. You've got the inclined plane, which we'll talk about later as well. But we're really just talking about accelerations, velocities, displacements at this stage. So in each case of these boards, you've got two sensors, one about there and one about there, for each of the three boards, and each of them feeds one of these meters. And we've got magnetic sensors and a magnet on our trolley. So it just tells us the time between probe A and probe B. 1 set, 2 set, 3 set. So what we expect to happen is longer time here because we're still accelerating, relatively constant time between the two, but maybe slower on the second one because it started to decelerate. And you're going to use those data, basically the raw data, the time A to B. We'll let you know the distance between the two probes, and it's up to you to then calculate from that the velocities at the different stages, and we'll calculate the average velocity at the bottom of the ramp using the acceleration through that period where it's accelerating. So we imagine that it's accelerating for this whole bit while it's on a slope because gravity's doing some work to accelerate it, and then it's relatively constant the rest of the time, except there's friction in the wheels that slows it. And we're going to use 3 different heights on this particular apparatus. The other thing that I'll just mention, this particular one comes from Serato, one of the lab manufacturing and supply places, but there are a number of different ways that you could do this. You could use some kind of other slope. You could use timing gates, light timing gates. You could even use a motion sensor that tells you the velocities directly. This one's kind of cool because there's a little bit of inference required. The students have to think through, what does it mean that I have this amount of time between these two incidences? The other thing I'll mention, we've got a wooden surface at the moment. We could also have a felt surface or a carpet surface or a rubber surface. I won't completely disassemble the apparatus to show you that, but there's a number of different surfaces with different frictional coefficients that we could use for this experiment. So let me run the car. It's going to go straight, and I can see on my meters 361 millisecond, 247 millisecond, and 270 millisecond. So you can read directly off from that it was going slower here. Remember that they're covering the same distance, so more time means lower velocity. So it took 347 seconds to get through that piece, only 247 to get through that piece. Sorry, 361, 247. And it took a little bit more. It took about 270 to get through that last piece. It had slowed down a bit. So I'll do one more at that angle, and then I'll change the angle. We'll also let you know what the angle is. So we'll just do some pretty basic trig measuring the height and the distance so that you know what that incident angle is. So on the second trial, 362, so very close to what we got before, 249, so very close to the 247, and 270, exactly what we got before, but in this case, the sensor has said it didn't get a sample. So it is the 270 we saw before. I think the car had gone off the track enough that we didn't get a measurement. So that's something we need to be aware of with these as well, is checking that we actually got a measurement. All right, let's try it with a slightly different angle. So exact same apparatus, exact same setup, but with a lower angle. So you can get the students to do a predict, observe, explain. They can say, well, I predict that because the angle is lower, the acceleration will be slower, the velocities will be lower throughout, or they could predict the reverse. Depends what they think is going to happen. So you can get them to predict and then explain what does happen. So if I run this one at this angle, it looks slower visually, but what do the data say? 421, we were getting in the 360s, 421. 287 we were getting in the 240s and 250s, and 60,000 milliseconds. That last sensor is not doing good things for us at the moment. I think, as I say, it's very difficult to make the car go straight the whole direction. We might try one more to see whether we can get it to go straight and get a reading on the last sensor. So we get 429, 297, and no, that one's still not very happy. Okay, and we'll just do one more reading with one more angle, one more set of readings. We would do in the lab with the students multiple trials at each height, of course, and then average our results. So let me run this one, and we can predict, based just on the trend, that it's going to be slower again. That would make sense. So we get 547, which is what we'd kind of predict, 390, and still 60,000. That one's given up and gone home for the day. That really is about all we need to get in terms of data from this experiment. There are a number of different ways we could measure it, as I say, but that will give us enough to graph velocities, graph accelerations, and determine the influence of the angle on the velocity and acceleration of the car. Not so much a calculation as an explanation on this particular one, because I've already done most of the calculations. The goal of this lab is mostly about actually drawing the motion graphs and making calculations using the graphs. There's a little bit of the physics of the inclined plane involved as well, but the main point is about drawing graphs. If I haven't emphasized the point already, the fact that I draw lots of freehand graphs in these videos doesn't mean that you should be drawing freehand graphs or even graphs on plain paper or just lined paper. You should be using a fine propelling pencil, a ruler, and graph paper for your graphs to make them very excellent and very accurate. So just quickly going through the situation that we had in the lab, we had an inclined plane section. We tried 3 heights, h, which we'll talk about in a second. The length of each plank was 1 meter, and it had sensors placed in it at the 0.25 and 0.75 meter marks, which makes the sensors 0.5 meter apart. So that's going to be an important distance for our calculations. And then we had a second plank on the ground and a third plank on the ground beside that, exactly the same, 1 meter with sensors at the 25 and 75 marks on each of those. So those were our 3 data sets, and we tried 3 different heights. Now, if we know that the hypotenuse of the triangle is 1 meter and the height is 0.16, 0.25 or 0.36 of a meter, we can use trig to actually calculate the basically cos is opposite over hypotenuse, turn that around a little bit and you'll get the relevant angles. Now what you need to do is calculate the uncertainties. I'd suggest that half the least scale deflection. So in this case, the least scale deflection is 1 centimeter. That's the 10 centimeter mark, that's the 1 meter mark. So we will, because there's 100 centimeters in a meter, it's not a normal SI unit that goes up in orders of 1,000. There's 100 centimeters, there's 1,000 millimeters. So we could work in millimeters if we wanted to, but we're working in whole meters. So it'll be 0.005, half a centimeter, 5 millimeters. Potential uncertainty in the height measurements depending on how precisely I use the ruler and so on, and that will apply to each of them. Then you need to think about how does that translate into the angle. You can't do the inverse sine of the uncertainty, but I would suggest proportional uncertainties. So the proportion that 0.5 is of 0.16, you'll have the same amount uncertainty proportional of 9.2. So that will give you your uncertainties in your angles, and you can work with those. So now they'll turn out to be your horizontal errors or horizontal uncertainties, which we tend not to put on the graph. So the ones that are going to be important in this case actually are the times turned into velocities. So we could suggest that there is some uncertainty in that 0.5 meter, probably on the same order, that it was about half a centimeter uncertainty in that as well. And that's, in each case, the distance that they travelled in these times that are in the table was half a meter. So the velocity is just going to be 0.5 in each case divided by the time in seconds. And so we've done the calculations, and I'll speak to that in a moment. So your result from this lab is going to be a graph. It's a motion graph. You'll do a velocity versus time graph. No, actually you won't in this case. You'll do a velocity versus angle graph, which is kind of an odd one. And you might be able to turn it into a velocity versus time graph. But initially, at least, you'll start with this because you've tried 3 different angles and you've got different velocities at each of them. The one that you should graph initially, I think, is this middle one. So I've actually named them board 1, board 2, and board 3. And so you can graph that, and there's a number of other things you could potentially graph to analyze this situation, because effectively what happened was it accelerated down the slope and then it slowed across this distance here. We'll talk about that in a moment. So the biggest angle we've got is 21 point something. So I'm suggesting maybe go to 25 degrees on this axis, and you'll have 9.2, 14.1, 21.1, somewhere along there. On this axis, you will have velocities between 0 and the largest one that we have in the table is about almost 3. So probably for scale, we're going up to about 3 on here. And so you will graph those. You will do vertical error bars, which will be in the velocity in this case. So in each case, you've got the 3 different angles. We did biggest angle first and then lower and then lower. And we only did 1 run on that lowest height. We just ran out of time and didn't do a second run. So we have only 1 data point for that. We have two data points for each of the 3 boards for the rest of them, although also on board 3, the sensor broke after the first trial. So we ended up getting less data. So board 3 is kind of sort of irrelevant. What we discovered was that it slowed down. So the velocity was 2.02 on board 2 meters per second and 1.85 meters per second on board 3. So there was a deceleration happening over the course of that. You could actually potentially extrapolate back from that and work out how much it decelerated between the sensors on board 2 as well. But that might be an extra level of analysis that would be a bit challenging, I think. So very quickly, you've got your times. These are just the times from the video, from our trials, and I yelled them out and they were recorded on the video, and then they're recorded in this table. So what I've actually done is there are the times for board 1, times for board 2, and time for board 3. And then I've turned that into the velocity, the average velocity for board 1. And I'm going to talk more to that in a moment. I'm going to talk about what this column is in a moment. For board 2, the velocities are that. So essentially, it was around about 2 meters per second at 21 degrees. It was around about 1.72 meters per second if you average those at 14.5 degrees, and it was about 1.28 seconds because we have nothing to average with it at 9.2 degrees. So you've got those velocities. What I'm going to suggest to you is that during its whole time on the board, the car was accelerating. So its velocity was 0 here, and it was something over 2 for the 21 centimeter height by the time it got to the bottom of the board. We don't know exactly, but we can assume that between there and there, it didn't slow down a huge amount. So, but what we actually get when we do the calculation is 1.39. But what I'm going to suggest to you is that if the acceleration is constant, then the velocity will, that number represents the average velocity in here. It will have been going slower here, faster by the time it got to the 0.75 center. So its average velocity, if it's constantly increasing, will be hit in the middle of that. Well, now we can extrapolate that and say that will be the average velocity for the whole length, right? This is a little bit conceptually challenging, but that's the average velocity in the middle, and the velocity is 0 at the start. So you would imagine if it's constantly increasing that the velocity will be twice that average value by the time it gets to the end of the board. So all this column is, the initial velocity at the bottom of the board is double that average velocity. So I've literally just doubled those numbers to get these numbers. Now what you might notice is some small changes to that V init column. For some reason my calculations were correct in some cases and not in others. I've just gone through and corrected all of those so that they are twice the value in the V average column. So hopefully that rationale and that logic makes sense to you, that the average velocity is reached in the middle between the two sensors, but that's also the middle of the board. And if the velocity is 0 at the start, then the velocity by the end of the board will be twice the average velocity. So I hope that makes sense. And so you can see that there is a reasonable, if that assumption is valid, then there is a reasonably strong acceleration. There it goes from about 2.78 to about 2.02, and 2.76 to about 2.01, 2.38 to about 1.74, etc. in terms of those. So again, you may want to critique that assumption. Think about the fact also that this is not a smooth transition. We didn't have a Hot Wheels track that made a smooth curve here. It was literally going from an angle to flat. So it may well lose some energy in that bumping down onto the flat surface, change of direction. So hopefully that gives you a sense, and your task, as I say, is to accurately graph our results, which may not be particularly accurate, but then again to be able to make an accurate estimation of the, actually do both, do the initial velocity and the board 2 velocity, that kind of middle velocity there. So graph these on a separate graph versus angle, and these on a separate graph versus angle, so that you've got some comparisons. And then you can also calculate the acceleration just on our assumption that the acceleration was constant. So effectively it went from 0, from rest at the top of the thing, to 2.77 meters per second by the bottom. What was its acceleration?